All right, so when you have your quiz score, make sure you record it on your folder next to your attendance check. All right, I already handed out the class notes for the day. We're working on class number 4. We're going to learn about linear combinations of vectors, how linear combinations of vectors relate to systems of linear equations, and a key concept we focus on is the span of a set of vectors. All right, so this little question that I wrote here for the demo is, I'm going to have you tell me what the answers are based on what you learned in the reading. Okay. So if u is the vector 1, 0, 0, and v is the vector 0, 0, 1, what does 3u plus 4v equal? 3, 0, 4. Good. So when you multiply a vector by a scalar, and what's a scalar? Just a number. Yeah, fancy word for a number. So when you multiply a vector by a scalar, like 3, you multiply every entry by that scalar. And when you add two vectors, you add them component-wise. So this would be 3u is 3, 0, 0, 4v would be 0, 0, 4, then add them component-wise. What is 3u plus 4v called? No. The CU, I don't know what CU is. Say that again. Something combination. Linear combination. 3u plus 4v is a linear combination of u and v. You can't say vector equation because there's no equal sign there, right? So you can't call it an equation. Yep. The arrow, yes. So for notation, a bold u is often written like that to mean vector. They both mean vector. Your textbook uses the bold. Actually, it'll be handy for me when I'm writing on the board to use the arrow because bolding things is annoying. So thank you for pointing that out. Oh, with the little hat. I haven't seen that one. No. Yeah. Yeah. All right. So 304 is a linear combination of 1, 0, 0 and 0, 0, 1. What would another combination be? Another linear combination. 2u plus 5v, sure. And that would come out to 2, 0, 5. What's the name for the set of all linear combinations of u and v? Span of u and v. So the span of u, v is the set of all linear combinations of u and v. So it's a set. And we have listed 2 elements of the set so far. 304 and 205 are both vectors that are in the span of u and v. They're linear combinations of u and v. What's another vector in the span of u and v? The 0 vector, that's a good one. So if I wanted to write that as a linear combination of u and v, how would I do it? 0u plus 0v. Yep. Zero u plus 0v is the vector 0, 0. That's in the span.
I did see in the book that there was a bold 0.
Yes. So the bold 0 means a vector with zeros in every entry. So this vector that I wrote 0, 0, I could also write as a bold 0 or a 0 with an arrow. Yeah. Oh, yes, sorry, these are 3 entry vectors. Yeah, 0, 0, 0. Thank you. All right, if I was going to write the span of UV using set builder notation, all the vectors in that are linear combinations of U and V, what do they look like? Some number, 0, and then some number. They all have 0 as their middle entry, right? Because no matter what you multiply U by or V by, you're always going to get 0 as the middle entry. So they look like some number. So I've written out 3 of them, 304, 205, 000. All of them has 0 as the middle entry. And the top and bottom number are not related to each other. They're just random numbers. So if I was going to write this in set builder notation, I would write, I should have given myself more room here. I would write the set of all 3 entry vectors, where the first entry is some number, we'll call it A. The middle entry is 0. And the third entry is some other number, not A, we could call it B, right? So it's a set of all 3 entry vectors with the middle number 0 and the top number some number, such that A and B are real numbers. A and B are elements of the real numbers. So this is kind of bringing back what we talked about on that first day of class when we were talking about set builder notation. So now we can use that notation to describe this new thing that we're going to work with called the span. How many elements are in the span of U and V? Infinite. Is the span of a set of vectors always infinite? Got a yes and I got some no's. Somebody give me an example where it's not infinite. Someone who said no. Span of the 0 vector. If I want to take the span of just the 0 vector with 2 entries, no matter what I multiply that by, it's always just going to be 0, 0. There's only one element in it. So it's not always infinite. There's one exception. It's always infinite except for this one exception, the 0 vector. Okay. No, there's no such thing as a null. It just doesn't exist, yeah. So any other vector, I could take the span of a single vector. Do this on another page. If I wanted to take the span of, say, the vector 2, 3. How many elements are in there? Infinite. There's only one vector, so I can't do any addition, but I can multiply this by any scalar I want. So this would look like, in, say, set builder notation, all these vectors would look like what? All the vectors in this set. Yeah. They're all going to be multiples, the same multiple of 2, 3. Just take some multiple of the vector. So you can multiply the vectors in your span by any scalar, and we're just going to call that scalar A. And when you multiply by a scalar, you multiply every entry in the scalar, and A is some real number. All right. Is the 0 vector always, sometimes, or never in the span of a given set of vectors? When is it not? If it's only sometimes, when is it not? It's always. Yeah. So you can always take all of your weights. That was your question, right? Those constants that you multiply the vectors by, they call them weights. You can always take all of your weights to be 0, and you'll get the 0 vector. So this is always. The 0 vector is always in the span of a given set of vectors. All right. Why is it always? Because no matter what vectors you're looking at, if you want to take the span is the set of all linear combinations, which means multiply them by scalars and add them together, right? If I take all my scalars to be 0, that's going to turn all those vectors into 0 vectors, add them together, and you get 0, the 0 vector. So if you take, if you're looking at all the linear combinations of a given set of vectors, 0 will always be in there because you can choose all the constants or weights to be 0. All right, so here are 3 questions that all mean the same thing. Is 4, 12, 4 a linear combination of 2, 1, negative 3, and 6, 5, negative 7? Equivalently, I could ask, is 4, 12, 4 an element of the span of 2, 1, negative 3, and 6, 5, 7? So being the span is the set of all linear combinations. So if you can show that 4, 12, 4 is a linear combination, you've shown it's in the span. And then the third way I could ask it, and this is only for 3 entry vectors, is 4, 12, 4 contained in the same plane as 2, 1, negative 3, and 6, 5, negative 7? Okay, so any 2 vectors in R3, right? And R3 means 3-dimensional space. Yep. Any 2 vectors in 3-dimensional space, if one is not a multiple of the other, determines a plane. So these 2, one is not a multiple of the other, so they lie in a plane. And we want to know, is 4, 12, 4 contained in that same plane? And that's equivalent to asking, is it a linear combination of those 2? All right, so to answer, we're just going to look at this one. Right. Linear combination, we have a solid definition for, so we can apply that definition. So we want to know, can I take a multiple of this vector plus a multiple of this vector to get this vector? So the multiple is what I don't know, so I'm going to call it x1 and x2, my variables. So can I take a multiple of 2, 1, negative 3, add to that a multiple of 6, 5, negative 7, and obtain the vector 4, 12, 4. Okay. Is there an x1 and an x2 that makes this possible? Right? If there is, then it's a linear combination, and if there isn't, then you can't write 4, 12, 4 as a linear combination of the other 2 vectors. Okay, so let's translate this thing that's called a vector equation. Translate it to a system of linear equations. Okay. When you multiply a vector by a scalar, you multiply every entry by that scalar. So this becomes the vector 2x1, 1x1, negative 3x1, plus, then multiply this vector by the scalar x2. So you get 6x2, 5x2, and negative 7x2. And that has to equal 4, 12, 4. And then when you add 2 vectors, you add them component-wise, right? So I get 2x1 plus 6x2, and x1 plus 5x2, and negative 3x1 minus 7x2. And that has to equal the vector 4, 12, 4. And for two vectors to be equal, what has to be true? It's not a trick question. For two vectors to be exactly the same, all their entries have to be the same. Yeah. So in order for these two vectors to be equal, their entries have to be equal. So this translates to a system of three equations. 2x1 plus 6x2 has to be 4. x1 plus 5x2 has to be 12. And negative 3x1 minus 7x2 has to be 4. All right, I have a system of equations, system of linear equations, two unknowns, three equations, two unknowns. How do you solve this kind of a system? Make a matrix and row reduce it. We use Gaussian elimination. All right, so the matrix, the augmented matrix that corresponds to this system of equations is going to be 2, 1, negative 3, 6, 5, negative 7, 4, 12, 4. So I'm going to row reduce this. I want to put this in reduced echelon form. Row reduced echelon form. So what do you want to do first? Flip the first and second, right? Because the first goal is to get a 1 in the upper left corner. So I could multiply the first row by a half, or I could just flip the first and second rows. Either one will get me a 1 in the upper right corner. So I'll just flop them. 1, 5, 12, 2, 6, 4, negative 3, negative 7, 4. And I would say I said row 2 swaps with row 1. All right, so now my next goal, when I'm doing row reducing, I've got a 1 in the upper left. I want all zeros beneath it. So I'm actually going to do 2 steps in one, right? I'm going to knock out both zeros in my in one. I'll write down what the 2 steps are, but I'm going to do them in so I don't have to write things a million times. So the only row that's not going to change here is 1, 5, 12. Okay. 3, I'm going to do 3 row 1 plus row 3 to knock out the 3 in the bottom. And I'm going to do negative 2 row 1 plus row 2 to knock out the 2. So I'll write them both down. I'm going to say negative 2 row 1 plus row 2 will be my new row 2. And 3 row 1 plus row 3 will give me my new row 3. So I'm going to get a new row 2 and a new row 3 in one step here. So let's just work on row 2. I'm going to multiply row 1 by negative 2, add it to row 2 to replace row 2. So negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times 5 is negative 10 plus 6 is negative 4. Negative 2 times 12 is negative 24 plus 4 is negative 20. So I've got my new row 2. And then to get my new row 3, I'm going to multiply row 1 by 3 and add it to row 3. So 3 times 1 is 3 plus negative 3 is 0. 3 times 5 is 15 plus negative 7 is 8. And 3 times 12 is 36 plus 4 is 40. All right. Next goal. Okay, so not get rid of, because when I say get rid of, I mean make into a 0. But you want to make that negative 4 a 1. You could get rid of the 8 first. You can do, I tend to make the 1s first, but you can get rid of the 8 and then make it a 1 at the end if you want. But I am going to make that negative 4 into a 1 by doing negative 1/4 row 2 to become my new row 2. So I have 1, 5, 12. Negative 1/4 times 0 is still 0. Then I get 1, and negative 1/4 of negative 20 is 5. And row 3 doesn't change. Okay, so now I want to knock out the 8. I want to get rid of that 8. I want to make it a 0. So what do I do? Yeah. Negative 8 times row 2 plus row 3 will give me a new row 3. Negative 8, row 2 plus row 3, new row 3. So rows 1 and 2 don't change. 1, 5, 12, 0, 1, 5. 1 and 2 don't change. Get a new row 3. Negative 8 times 0 is 0, plus 0 is still 0. Negative 8 times 1 is negative 8, plus 8 is 0. And negative 8 times 5 is negative 40, plus 40 is 0. Yeah, so we now know there are infinitely many solutions, and I'm in reduced echelon form. Well, I'm one step away from reduced echelon form. What would I do if I wanted this to be in reduced echelon form? Knock out the 5 that's above the 1 in the middle column. So let's just do the one more step, just for practice. We have completed the forward phase here. The backward phase then is to get rid of the numbers above the pivots. All right, so to get rid of that 5, I would multiply row 2 times negative 5 and add it to row 1. So negative 5, row 2, plus row 1 gives me a new row 1. So 0 times negative 5 is 0, plus 1 is still 1. Negative 5 times 1 is negative 5, plus 5 is 0. Negative 5 times 5 is negative 25, plus 12 is negative 13. And the others stay the same, 0, 1, 5, and 0, 0, 0. So now I can read solutions off of here, and it says x1 is negative 13, x2 is 5. There is no x3, right? Because there were 3 equations with 2 unknowns. So this was, we had more information than we needed. Yeah. So remember what we were trying to solve. If we go back a page, we were trying to solve this system of equations. And this system of equations came from this vector equation, right? If you can find an x1 and an x2 that makes this true, that means that these two vectors form a linear combination to make 4, 12, 4. So the answer is yes. 4, 12, 4 is a linear combination of 2, 1, negative 3, and 6, 5, negative 7, because we found weights, x1 and x2, to use to combine them in a linear way to make our vector. Yep. That doesn't always mean infinitely many solutions. Yeah. Doesn't always mean that. If you have the same number of equations as unknowns and you get that, then it means infinitely many. Okay, so the answer to the question was yes. The vector was a linear combination of the 2 given vectors. The vector is an element of the span. The vector is in the same plane as the 2 given vectors. It's yes, yeah. If there is a solution to this system, it's yes. Sometimes there are infinitely many solutions. Sometimes there's more than one x1 and x2 that can make the linear combination. The only time you would say no is if this bottom row tells you that the system's inconsistent, right? If you get like 0 equals 7, something like that. Okay, so I think that that's a good place for you to start on the group activities.